Let's say you're given the diagram here of a mass on a spring between 2 points x1 and x2, and the question wants you to find the velocity of the mass at point x1. To solve, we need to apply the work-energy theorem to the system. From the work-energy theorem, we know that the total work is going to be equal to k2 minus k1, which can also be written in this form here. And the theorem states that the total work done by an object is equal to the change in its kinetic energy from point 1 to point 2. Also, from last time, we know that the total work done by a spring force is equal to the negative change of the elastic potential energy given by this equation here. So if we equate the work done by the elastic potential energy to the total work from the energy theorem, we get this expression here. And then we can isolate for point 1 and point 2 by bringing this term to the right hand side and then this term to the left hand side. And if we do that, we get this expression here. So this equation represents the energy for the spring system between the 2 points, which we can also write more generally in this form here. So if only elastic force acts on the object, the total energy is conserved, where U elastic 1 and 2 are the elastic potential energies and K1 and K2 are the kinetic energies. So we can apply it to our example. So our example here, and this is our energy equation. If we plug in the kinetic energy equal to 1/2 mv squared and the elastic potential energy equal to 1/2 kx squared, we get this expression here. We can multiply the whole thing by 2 to get rid of the 1/2 from each term. And then we can identify our variables. So we have K equal to 50 newtons per meter. And then V2, if we look at our diagrams, equal to 4 meters per second. And then X1, if we look at our diagrams, equal to -5 centimeters. Also, X2 is going to be equal to -2 centimeters. Then if we look at our units, the velocity and the K is given in meters. We should convert x1 and x2 into meters as well for the units to make sense. And then we also have the mass equal to 1 kilograms. We are trying to solve for V1, that's our unknown. So we can plug all these in. Start by computing the term on the left-hand side here, computing the units and the amplitudes, and then we can do the first term on the right-hand side. Also making sure to compute the units and the amplitudes, and do the same thing for the second term on the right-hand side. And if we plug all these values in, we get this. We can isolate for V1 squared by bringing this term to the right-hand side, and then we can do a simplification, summing the terms on the right. Do that, we get this expression here. We can isolate for V2 squared by multiplying both sides by 1/kilograms. So on the left-hand side, the kilograms cancel, and we get this expression. We compute the units on the right-hand side. We left with meters squared per second squared, which makes sense. And square root both sides and get the final answer for the velocity. So this is going to be the velocity of the spring at point x1. So if we look at our diagram here, at point V2 it's 4 meters per second, and then at point V1 is 3.98 meters per second. And this answer makes sense since the velocity at V2 is greater than V1. That aligns with the work energy theorem because at point x1 the spring is more compressed, which means that the system is going to have more elastic potential energy at this point. And as the object moves towards the equilibrium, this elastic potential energy is converted into kinetic energy, which means that the object speeds up, and that's why we see this behavior.